You're a high school chemistry teacher, and you're ready to tackle the concept centered around reaction rates. How can you speed up a chemical reaction? What factors can slow down a given chemical reaction? But you want to connect this concept to a phenomenon, namely, what is currently happening to our coral reefs. This is footage that was edited by my son back when we took a snorkeling trip to the US Virgin Islands, in particular St. John's. As a result of the increasing ocean temperatures, what has the effect been on our coral reefs? So when you introduce this phenomenon centered around coral reefs, the question that really comes to mind is, why are coral reefs so important? So 3 key things come into mind. First of all, coral reefs support a vast variety of marine life that is so incredibly varied in terms of its species diversity. Second, coral reefs protect coastlines from erosion and storms. So not only are they important from a biological perspective, they are also maintaining the geography of planet Earth at these coastal areas. Thirdly, coral reefs contribute hugely to our tourism and fisheries. According to NOAA, the National Oceanic Atmospheric Administration, the fisheries encompass in the US about $100 million. The value of our coral reefs tourism is much, much more than that. The second question that comes to mind is, what is coral? Coral is an invertebrate animal. Animal because if you look closely at the individual cells, they lack a cell wall. So even though corals are sedentary, because they're connected to their base, they are not considered to be plants. Corals secrete a calcium carbonate skeleton, CaCO3, very similar to the chalk for those teachers that are still using chalk. Third, the coral itself has a symbiotic relationship with an algae, namely the zooxanthellae. These algae contain chloroplasts and as a result can do the process of photosynthesis. In the presence of carbon dioxide and water, and of course solar energy, photosynthesis results in the production of sugar, and the coral is able to use that sugar released by the zooxanthellae. But something has happened to our coral reefs across the world. What causes the coral bleaching? These 3 pictures were taken of the National Marine Sanctuary of the American Samoa. The first picture shows you very healthy coral. The picture in the middle obviously is not looking so good. It's very bleached, much like my shirt. The third picture, although similar to the first, it's actually coral that is now considered dead. The photosynthetic zooxanthellae have left their symbiotic relationship with the coral animal and as a result can no longer support the ecosystem. This bleaching, which is a result of the zooxanthellae being expelled from the coral, is caused by the increasing ocean temperatures. And this bleaching can further be exacerbated by ocean acidification, which could be caused by the increased carbon dioxide present in our atmosphere, which means higher carbonic acid levels in our oceans. So after introducing the anchoring phenomenon centered around coral reefs, we're now ready to actually delve into the actual lab activity. There are 2 parts to this lab, and then in the end we'll connect it back to the coral reefs. For the first part of this lab, students are to determine the molar concentration of hydrochloric acid. Let me show you what that looks like. Students start with 50 milliliters of 1 molar hydrochloric acid, and they use a large marble chip. By making use of these few basic measurements, the lab handout then guides students through some easy calculations with the final goal to determine the molarity of the starting hydrochloric acid solution. They can then compare that to the accepted value and see how well they actually carried out the lab. What causes their error? What is the percent error? What might be the explanation to any differences that they've observed? But the second part of this lab is really what connects it back to what may be happening at coral reefs. We are again focusing on reaction rates. What factors could we change to speed up a chemical reaction? And we can relate this second part directly to what may be happening at coral reefs in terms of increasing ocean temperatures. For this part, the baseline again is 50 milliliters of 1 molar hydrochloric acid. Instead of using the marble chip, I give my students half a piece of yellow chalk because it's such a sunny color, and then students record the time until they've produced about 50 milliliters of carbon dioxide collected in the graduated cylinder. Let's watch how that works. For the first experiment, my students are using half a piece of chalk. They're breaking it into smaller pieces with the help of a mortar and pestle. They are conducting this reaction at room temperature. Next, they are going to fill the graduated cylinder with tap water. Turn it upside down into the tub, add the hose into the graduated cylinder to capture the CO2. They use 1 molar hydrochloric acid, 50 milliliters of that. Once added to the flask, they add the chalk, cap the flask, and watch the CO2 produced. This second reaction makes use of just the half piece of chalk, but not broken into smaller pieces, and a higher concentration, 1.5 molar, of hydrochloric acid. The third reaction uses 1 molar hydrochloric acid, but at an elevated temperature, and a half piece of chalk. Upon completion of these 3 experiments, condition 1 with small chalk pieces, condition 2 with 1.5 molar hydrochloric acid, and condition 3 using an elevated temperature, namely 50 degrees Celsius. Let's now look at the quantitative data in Google Sheets. When I do this lab, I make sure that I divvy up my class into 3 different groups, and each group is responsible for their chosen variable, so that we can then pull the data from everybody in the class. This graph shows you reaction rate as a function of the molarity of the acid. On the y-axis, you see the rate expressed in 50 milliliters of carbon dioxide per time in seconds, and on the x-axis, you see 50 milliliters of hydrochloric acid used, but at varying concentrations. This is a very nice linear relationship, as shown by an R-square value of very close to 1. Nice data. This second graph represents the relationship between reaction rate and the size of the chalk. Again, we used half pieces of chalk, and then the students could choose how small they wish to make that chalk. Really fine using the mortar and pestle, or somewhat less fine pieces. Why is the relationship here not so nice as the one in the previous graph? That's probably because it's really difficult to break down that chalk into ever decreasing pieces. And so it's great when they're not getting always that perfect data out. It gives you that opportunity to see, why are we not getting a higher R-squared value? For example, had we used the reaction between magnesium and hydrochloric acid, it's much easier to break a long strip of magnesium into ever smaller pieces. And that's why this third graph is even more fitting, because that is how life works. You don't always get that perfect data that one would like to see. What the students might have liked to see is if you keep on increasing the temperature of the hydrochloric acid, then you would see that the speed by which the carbon dioxide is entering that graduated cylinder would go up as well. But clearly, we're not quite seeing that. Instead, there is an optimal temperature, could be roughly 50 degrees Celsius. And again, there's not really enough repeated data to make sure that this is indeed the perfect trend. But there is a point where the temperature was simply too high, maybe because hydrochloric acid solutions is really hydrogen chloride, which is a gas, in water. And at those higher temperatures, maybe some of that hydrochloric acid is actually escaping the aqueous solution. If we now reflect on our data that we obtained from the high school chemistry classroom, and we relate it to what is happening at our coral reefs, then we can certainly think about what increased ocean temperatures could do to this beautiful ecosystem. Increased ocean water temperatures could certainly have a great effect on this delicate ecosystem, and that would be a shame. What are the actual standards that we are hitting with this particular lab? Let's take a look. The Next Gen Science Standards and the New York State Science Learning Standards are centered here around HSPS 1-5, collision theory and rates of reactions. The higher the temp, the faster those collisions. the greater the rate of the reaction. But we saw in our experiment that we're not necessarily seeing that perfect trend. Another set of standards that's addressed with this lab is the HSPS 1-2, simple chemical reactions. We are simply combining calcium carbonate, that's our chalk or our marble chip, with hydrochloric acid. That is a double replacement reaction. You're releasing carbonic acid and calcium chloride. And the carbonic acid is really the release of carbon dioxide bubbles into the graduated cylinder. Now, we may also touch upon a third standard, namely HSLS 1-5, from molecules to organisms, structures and processes. And that is because when we were discussing the coral reefs and their symbiotic relationship with the zoocentellae, then we are also having a conversation about the photosynthesis process. So one way to expand this lab is by actually having them create this model that centers around coral reefs and how the zoocentellae live in this symbiotic relationship and really diving into that photosynthetic reaction. And to bring it really down to the basic level, this lab certainly addresses HSPS1, matter and its interactions. Now, if you're interested in receiving this handout, as well as the student videos and the teacher keys, go to the description below this video, and in exchange for your email, you will receive this Google Doc with all the lesson materials. In conclusion, I have shown you here how you can use coral reefs as the anchoring phenomenon for reaction rates, a key concept in the high school chemistry curriculum. Dutch lesson for today. Coral reef in Dutch is called koraalrif. Repeat after me. Koraal obviously means coral. Rif means reef. Put the two words together because Dutch people love to stick words together. It's coral reef, koraalrif. Thank you very much for watching. Bedankt voor het kijken. Tot ziens and see you in the next video.